Our test is on Friday. And if you look on our list, I told you I would be very specific about which ones are going to appear on the test. So the new ones shall be, I'm looking at my list right here, I believe number 18 was the first of the new ones. That's the efficiency gap through number 24 on the list. So maybe I will just shout out these topics just so that everybody knows what I'm talking about. Number 18, all right, I can write them down. 18 was the efficiency gap. 19 is the convex hull ratio. 20 is the isoperimetric quotient. I hope you are okay with my abbreviations here. Of course, anybody, you should all have this list, so you can look it up if you like. 21 is very basics. So here, these are the graph theory questions. 21 is just called, on the list, it's called paths, degrees, connectedness. So this is just very basic questions about graphs, what a path is, what the degree of a vertex is, what it means to be connected. Those, you should expect the question for this topic to be very easy if you know what you're doing. Number 22 is what I call imagine a graph. So these will be similar to, there were, I think, 3 questions like this on the homework that's due tomorrow. So check those out for an idea of what that is supposed to mean. I would give you some kind of a description of a graph in words and then ask you questions about the properties of this graph, about the degrees, about is it connected or not, that kind of a thing. Unfortunately for some people, doing these questions well, you will notice this on the homework, requires that you read the words and understand the words. This can be difficult sometimes. I mean, I'm not trying to be cryptic about it, but you've got to read the words. Okay, number 23 is also, in my opinion, a very easy one. This is the formal description of a graph. There are some on the homework about this. This is just writing a graph as a set of vertices and a set of edges. Or the other way around, if I show you a graph, if I show you a set of vertices and edges, can you draw me a picture of the graph? If you know what you're doing for those are also very easy. And then number 24 is about Euler circuits and paths. So this did not appear on the homework because we just started talking about it yesterday, but I figure I might as well put one on the test. I mean, if you get it, then that's great. If not, as always, you can try it again next time. So Euler circuit and path, do they exist? They're kind of two separate questions, as I mentioned last time. There is the question of does it exist or not, and also the question of how do you actually draw it, or how do you find the Euler circuit if you know it exists. That's a separate issue. As for this, number 24, it's just about do they exist or not. And we're going to talk more about this today. Are there any, anything anybody wants to talk about concerning the test? I hope that all of these are things that you remember how to do. You might want to refresh your memory a little bit on some of them. But if you do the homework for tomorrow, that's basically all of this. So if you feel good about the homework, or if you're wondering, if you're not sure how good you feel about these things, try and do the homework. If you feel good about the homework, you should feel good about those, at least those ones. And then the previous 3 were from the homework last time. Any questions about any of that? All right. Please let me know if you're unsure about which of the old ones you have credit for. You should be trying to get credit for the old ones which you have not yet done. And I would be happy to chat about any of that stuff. Although, as I said, unfortunately, I'm not going to be around tomorrow. But send me emails or something. I can try my best to help out. And I will be around today. Okay, great. Let's get on with it then. Here ends the announcements about all of that stuff. Let's talk some more about Euler circuits and paths. Remember, an Euler circuit is one which covers every edge in the graph without repeating any. And an Euler path is like that, but it's not a circuit. So circuit means it starts and ends at the same point. A path means that it starts at one spot and ends at a different spot. So like for instance, one of the examples we talked about last time was this kind of Triforce graph. Does it have an Euler circuit? Does it have an Euler path? I hope you remember the sort of the trick for this, the rule. You look at all the degrees of every vertex. Remember, the degree is how many edges touch that vertex. So here is a degree 2. Here is a 4. This one is 4 because it's 1, 2, 3, 4 edges right there. 1, 2, 3, 4. This one down here is a 2. In this example, they're all 2s and 4s. In here on this graph, we see that the degrees are all even. These are all even. So that means there is an Euler circuit. That means it is possible to make a path through the graph which starts and ends at the same point. That's what it means to be a circuit. And the Euler part means it uses every edge once without repeating any. And if you wanted to, like, I could. Now this is a separate issue which I'm not going to ask you to do on this test because we haven't really gotten into it. But how could I draw this? I'm just going to try and draw a path that goes around every edge once without repeating any. And I think I did it, right? This path covers every edge once without repeating any. There are many ways you could do that. It's not just one way to do it. But that is the drawing of an Euler circuit. All right? So I will refresh our memory about the rules from last time. This is a theorem proved by Euler. Euler sort of invented all of this stuff. It says if all degrees are even, then there is an Euler path, Euler circuit. And the other rule about paths, if all degrees are even except for 2 odds. Then there is an Euler path. Right, this is the theorem. If all the degrees are even, there's an Euler circuit. That was the case in this this example up there, right? Those are all evens. And if all of them are even except for 2 odds, then there is an Euler path. All right. So I have some examples just to get us started, even though it's been 10 minutes, but that was all sort of a review. Just to make sure we're all on board here, how about I would like you to tell, I have some examples here. Sorry. Draw like this. Sorry to make you copy my pictures here. So here, all of the intersections are meant to be vertices on this picture. Like so. All right, I would like you to tell me, does it have an Euler circuit? Does it have an Euler path? Does it have an Euler circuit? Does it have an Euler path? Right. And then I have some more. So that's one example. How about another one here? And I got one more. All right, see what you think. I'm going to walk around and see how you're doing. Hopefully you can correctly copy my pictures. Circuit. Yeah, circuit is when they're all even. Path is when they're all even except for two lines. All right. This is not the same as mine. But for each of these graphs, you should be answering two different questions. Don't just say one yes or one no. It's, does it have a Euler circuit, yes or no? And also, does it have a Euler path, yes or no? Okay? There are three dots, that means
this is the same formation. Right?
yeah.
Okay.
Your answer to each question is no.
Okay.
No circuit also.
Got it.
Doing all right here? Yeah, so but this is not 3. It's a 4. It's 4. Yeah. Let's go on. All right, can we talk about these? It looks like people are doing all right. You must be able to easily identify the degrees. This is, you have to learn how to properly count the degrees. Like this point up here, the top of this one, is a 3 because there are 3 edges going into that vertex. This one here is a 2. This is also a 3. This is a 3. This is a 2. You're looking at how many edges go into that vertex. In the middle on the bottom, how many edges? 1, 2, 3, 4, 5. So this is a 5. This guy right here is also a 5. This is a 5. This right in the middle there is a 4. All right? So I hope you got those numbers for this graph. And what are the answers to my question? Does it have an Euler circuit? Euler circuit means they're all even. So no, this one does not have an Euler circuit because they're not all even. So no Euler circuit. Does it have an Euler path? Also no. Euler path means they're all even except for two odds, and that is not the case here. I have more than two odds. So it has no Euler circuit and also has no Euler path. I hope that's what you said. If you count up some of the degrees wrong, you're going to get the wrong answer. So you will want to make sure that you are getting the degrees correct. All right, how about the one directly beneath? These ones, the degrees are 2. That's a 3. That's a 2. A 3, a 2. This one right here is 4, because I see 1, 2, 3, 4 edges around that point. Here is a 2, another 4 there, and in the middle a 4. So I hope you got those numbers. And in this case, what do you say? Or is there an Euler circuit? Show me the thumbs. The thumbs should go down. Yeah, there is not an Euler circuit because they're not all even. So no circuit here. No Euler circuit. How about path? What do you think? I think thumbs up for the path. Remember, path means they're all even except for two odds, and that is the case here. I see two odds, the 3 and the 3. So no Euler circuit. There is an Euler path, though. Right? Great. And this one over here. So this one, when I draw the degrees, they are, oops, that's a 4. This down here is a 4. That's a 3, and a 2. I think I did those right. And again, in this case, I see two odds and the rest even. And so that means there is no Euler path here. No Euler circuit. Yes, there is an Euler path. Because Euler path requires two odds and the rest even. All right, fantastic. Any questions about that? I have 2 more cute examples, which I have on handout, although it hardly deserves to be a handout, but just so that you don't have to draw these big and somewhat big and complicated pictures. This will only take us a moment to discuss. I do like to do examples that are a little more complicated than just these sort of small graphs here. All right. And I will try to put this picture on here. Sorry, I forgot to prepare this picture. I hope I have it in my photos. Come on now. Oh, I have these separately. All right. Let's talk about Pac-Man first. So the first thing, everybody got one? I hope. All right. The first thing is, this is the standard Pac-Man board. I hope you're all familiar with Pac-Man. Pac-Man is this fine fellow right here. He has a nice lady friend named Ms. Pac-Man, which is a superior game. That was the sequel. That was like Pac-Man 2, was Ms. Pac-Man. And your goal in Pac-Man is to eat all of these little dots here, and also the big dots. The big dots are like a power-up, and you have to avoid being killed by these guys, the ghosts. But anyway, the question that everybody wonders from time to time, if you play Pac-Man enough, I would like to ask, is it possible for Pac-Man to just run around the entire level to eat all the dots without ever retracing any steps? Retracing any steps. This would be like the theoretical most efficient way to play Pac-Man, is if you could just walk around constantly eating the dots and never go back across a place where you have already been before. That would be the best way to play. Is that actually possible to do that? We can answer this question by viewing this as a graph. I would like to turn this whole thing into a graph according to, and I'm going to draw sort of like a roadmap type graph. So I'm going to draw, and hopefully you'll be able to see this on my picture here. I'm going to draw edges just following where the dots are, right? Because these are the places where Pac-Man needs to go. And remember, the question is, this would be like the best possible way to play this game would be if you could somehow cover all of this ground without ever retracing any steps, because of course you want to finish as fast as possible because the ghosts are trying to kill you. I don't know if they really kill him. Anybody know the Pac-Man lore? They do something to him that he doesn't like. You can assume they kill him. I don't know. So that's the graph that I'm imagining. And the question, is it possible for Pac-Man to go across all of this territory without ever retracing his steps? That's actually the same as Euler something or other, right? Am I looking for, this is about an Euler, am I looking for an Euler path or an Euler circuit? Euler, these things, it just means you're going to cover all of those edges without ever retracing your steps. But am I looking for a path or a circuit in this case? Remember, the difference is a circuit will end where it started. A path does not necessarily end where it started. Anyone familiar with Pac-Man? Do you need to do a circuit in Pac-Man? I didn't say anything like that. And yeah, it's not part of the game. You don't have to start where you finish in Pac-Man. So I am looking for an Euler path. The goal is simply to cover all of this, all of those red lines without ever going back over any. So can anyone say, is there an Euler path in this graph? I see some shaking of the heads. The question is about the degrees, right? So look at the degrees, and we actually don't have to do all of them. There are many intersections here, right? There's a 3. This right here is a 3-way intersection. There's a 3. Here's a 4. There's a 3. There's another 3. There are actually many 3s in this graph in terms of the degrees, right? I don't think we need to draw them all. There are many 3s in the maze. That's what they called this. And what that means is, because we have many 3s, more than 2 3s, there are many odd degree vertices, and so there is no Euler path. And I would just say we have many odd degrees. Many 3s. Actually, there are no 5s, because you're not allowed to have diagonals in Pac-Man. Many odd degrees, so there is no Euler path. And actually, the people who created Pac-Man actually were aware of this fact, and they specifically designed the maze to have a lot of 3-way intersections so that there was not just sort of one best way to play it. Because otherwise, if there really was an Euler path, then everyone who plays Pac-Man would just memorize the way to go around, where you never retrace your steps. But they purposefully designed the layout so that there is no such thing as like the best way to run around the maze. Right? Any thoughts about that? Great. So that's my cute little Pac-Man example. How about the other thing on the paper is the lines, the standard lines on a basketball court. So I got that one here also. Allow me to scroll here. I am going to try to ask a similar thing. Let's imagine that you are the guy who paints the lines on a basketball court. And the natural question to ask here is, if we're painting the lines, I have some sort of like a paint machine on wheels, I guess is how they do it. I don't really know how they do it, but I imagine somebody is like walking around here painting each little bit. If I'm painting the lines, I want to ask a similar question. Can I do it all sort of in one go without ever retracing my steps? Without retracing my steps. If I'm pushing around like a painting machine, there are good reasons why I don't want to walk across the part that I've already painted, right? This, again, is basically the same question, right? if I view this whole picture as a graph where these things are like, these little intersections of the lines are vertices, the same, it's really the same question as I was asking about Pac-Man. Can you go across all of these lines without ever retracing your steps? What do you think the answer is? Show me the thumbs. Yes, yes, it is possible, or no, it ain't. I think the answer is no, it ain't. What you should be looking for here is the degrees. If they're all even, or maybe they're all even except for 2 odds, then you can do it. But if there's more than 2 odds, you can't do it. And there are more than 2 odds. In this graph, if I were to write the degrees, like that one up there at the top is a 3, and also at the very bottom is a 3, but there's even more 3s. There's a 3 over here, over here, over here, over here. There's many odds here, right? Many odd degree vertices. Many odds, so there is no Euler circuit or path. And that means the guy who paints the lines, or the young lady who paints the lines, must at some point turn the machine off and either go outside the lines, like you might sort of get stuck here and then you just have to walk over there without painting a line, or you might have to retrace your steps across a part that you already painted. All right, no Euler circuit or path in this graph. So this kind of scenario, you can see this kind of situation arising often in real life. Typically not in like really important things, but in sort of cute little things like this. All right. Great. I have just a couple more examples, and maybe that'll do it for today, or maybe we can start talking about the next thing on the big list. A couple more examples. How about, this is similar to the basketball and the Pac-Man thing. Let's think of a network of roads, like, I'm trying to draw nice straight lines here. Something like that, all right? And let's say this is a street network, and Mr. Plow wants to plow the streets of course, without ever retracing any. You want to drive your plow down the street that you already plowed. That's the idea. Mr. Plow wants to plow the streets without retracing any. Is this, and let's say he wants to start and end, starting and ending at the same vertex. Is it possible? Well, again, you would look at the degrees here. I see 2, 3, 2, 3, 3, 4, 3, 2. I hope that everybody is used to just looking at things and saying what the degrees are. This is a skill that you will want to practice on if you're still a little shaky on writing those numbers down. Is it possible to do this plowing scenario that I described? I would say it is not possible because I see many odds here. So we have many odds. So it's not possible. What about what about if he doesn't care about starting and ending at the same point? So there's many odds in this picture. There's 4 of them here. So it's not possible, and in fact, it's not possible even if he starts and ends at different points, right? All right. Here's a cute, plot twist. Mr. Plow has a nice lady friend. Let's call her Ms. Road. She wants to make his dreams come true. And Ms. Road has the ability to build new roads. Ms. Road can build 2 new roads to make Mr. Plow happy. Can anybody say, actually, it is possible, if you're allowed to add 2 new roads, can you make it so that Mr. Plow can live out his dream of driving around each road once without repeating any? Anybody see how this is possible? I'll give you a hint. I'll tell you where one of the new roads should go. So I'm going to draw the same picture here, but I'm going to add 2 new lines to it. Now the degrees, keep in mind, are 3, 3, 3, 3, 2, 2, 2, and a 4 in the middle. Check it out. I am going to add a new road here. Why did that road make things better for Mr. Plow? It's because since I add that road, this degree, it used to be 3, but it's now 4 because now there's another edge touching that vertex. And this degree up here is also now 4. Right. Can anyone suggest where you could add 1 more road to make it, you want to make it so that you can actually drive the plow across every road with no repeats and starting and ending at the same point. Anyone, can anyone suggest where should I put in another road? Yeah?
And the same thing with the 2 3s.
Yeah, another diagonal connecting the 2 remaining 3s. If I put another road like that, now this becomes a 4 and this becomes a 4, and now they're all even. So building new roads can change some of the degrees. You can't just put them anywhere though. In fact, if you put them in certain places, it'll get worse. You could, if you, for instance, if you decided to put a diagonal there, you would have taken 2 evens and made them odd. But here I'm adding diagonals to make some of the odds into evens. So now all degrees are even. So there is an Euler circuit. Right? In other words, now it is possible for the plow to do what he does best. So now Mr. Plow can do it. All right? I hope that folks are feeling all right. I don't think we need to do any more examples of these, but this is the kind of thing that you should expect to see on the test about Euler circuits and Euler paths. It's all about the degrees, and are they all even, or are they all even except for 2 odds? All right. Any questions about those guys? These will be on the homework for next week, but you know, ordinarily I don't like putting stuff on the test that wasn't on the homework assignment, but I figure you might as well do it, and you might get it right. And if not, you'll have another shot at it next time. All right. Great. Let's talk. We have a few more minutes. I think we can start talking about the next thing on the list. So this, you know, what I say for the next 12 minutes will not appear on the test, but this is about the next item on the list, which is called, this is another graph theory theorem from Euler. Euler's sum of degrees theorem. I'll get a little intro today, and then we'll talk more next time, which I guess will be next week on Tuesday. Euler's sum of degrees theorem. This is another of Euler's original graph theory ideas. So I would say this is a little less famous than the theorem about Euler circuits, but this is also something that comes up in real life every so often, the sum of degrees theorem. I will just refresh our memory. One way to summarize what we were saying about Euler circuits and paths is the number, it's all about the number of odd vertices. If there are 0 odd vertices, that means there is an Euler circuit, right? If there are 2 odd vertices, there is an Euler path. This is what we've already said so far. And then if there's any more than two, then there is neither, right? That's what we've been talking about all today. There is, though, sort of one thing left out right here, sort of in between, right? What if there is only one odd vertex? Actually, we have never discussed that situation. What if there's only one odd? If there are two odds or more than two odds, we know what to do. But what if there's only one odd? Only one odd vertex. I mean odd degree, right? Could I just give you maybe 2 minutes? See if you can draw an example of a graph which has one odd degree vertex. Can you draw a graph which has only one vertex with an odd degree? Just to get us started. I'll give you until 9:42. Actually, I'll give you until 9:41. Oh, it says 9:41. Your time is up. I gave you not much time because this is actually impossible. I saw some attempts as I was going around. This was my little prank. A graph with only one odd degree actually is impossible. This is not obvious. It's not obviously impossible. Like when I suggested that you try this, I don't know what you were thinking, but I don't think anyone said, "How dare you ask me to do that?" It's something which is obviously not possible to do. It is not possible, but I wouldn't say it's obviously not possible. Like maybe, if I were trying to do this, I might start off like this and say, okay, that's a degree 1. Now I'll just like add stuff to the rest of it so that 1 is the only odd and then everything else is even. But if no matter how you try to add stuff to the rest of it, maybe like that, this is a 2 and that's a 2, but now that's a 3, so I have 2 odds. You will find if you just sort of try over and over again to do this, it is not possible to have a graph with only one odd degree. And if you ask me why is that impossible, I would say it's because of Euler's sum of degrees theorem. So this is the appropriate way to think about this thing. I will tell you what the theorem says first, and then we can say it's once it's explained, it's not very complicated. But this is Euler's sum of degrees theorem. What it says is, in any graph, the sum of all the degrees is always even. This is a true fact about any graph that Euler realized. In any graph, the sum of all the degrees must be even. This is true of any graph. The sum of all the degrees is always even. Another way to, that's all I want to say. The sum of all the degrees is always even. So what this means, if you think about it, this means there cannot be only one odd, because then if you were to add up all the degrees, you'd have only one odd plus a bunch of other evens, but then they would add up to an odd. That's because an odd plus a bunch of evens, it will equal an odd. So in any graph, the sum of all degrees is always even. What that means is, so there can't be only one odd and the rest even. Just because of the way that like odds and evens would add together. If there's only one odd and the rest even, then when you add them all together, you're going to get an odd, because an odd plus an even is an odd. All right, these are some basic, number facts. I don't know if you are hip to, if you remember all of these facts, but take my word for it. If you don't, I'm telling you, there can't be only one odd and the rest even, because then it would all add up to an odd, and the sum of degrees theorem says the sum of the degrees must be even. It is possible to have two odds and the rest even. I mean, we've seen many examples of that. That's because those two odds will add up to an even, and then it is still true that the sum of all the degrees is even, all right? So there can't be only one odd and the rest even. In fact, you can say, I will write this as, this is a fancy word that mathematicians use, corollary. This means another sort of a thing which follows as a consequence from the main theorem. For exactly the same reasons as I'm saying, there can't be only one odd and the rest even. Actually, there cannot be an odd number of odds, because if you add together an odd number of odds, it adds up to an odd, and this is not allowed. It has to add up to an even. That's what the theorem says. So this is a little confusing to write it this way, but it says the number of vertices with odd degree must be odd. That's what it says. This may be a little confusing, but when you look in it, not odd, sorry, even. Right? If you're talking about how many odd vertices there are, there can't be just one. There can be two, but there can't be 3 or 5. The number of vertices with odd degree must be even. It's because they have to all add up to be an even, and so the number of odds needs to be even. If you have an extra odd, it'll all add up to be an odd. This actually implies weird facts about real life, which I find very mysterious and kind of strange but true, kind of whiz-bang, interesting facts you can tell your friends about at the club. This means, for example, if you think about graphs which arise in, let's say, like social networks. Let's think about Facebook as a simple example. I mentioned Facebook because Facebook has the most convenient structure as a graph, because if you're friends with someone on Facebook, then automatically they are also friends with you. I don't use Facebook, but I'm pretty sure that's how Facebook works, right? This is not true. Like on Instagram, you can follow somebody even if they don't follow you back, and so the connections don't really make a standard graph because they're sort of like one direction but not the other way. But anyway, on Facebook, everybody has a certain amount of friends. So on Facebook, let's say I don't actually use Facebook, but let's just imagine I have a number of friends, right? It tells you that somewhere, right? You have 3 friends. That's my lame Facebook following, right? I have some number of friends. That number of friends represents the degree in the graph, right? That number is my degree in the graph. And if you think about overall, like all the people in the universe on Facebook, what are their degrees? The degree is just how many friends you have, and there's no reason for that number to be even or odd. Like I could have 7 friends, or I could have 8 friends. There's no reason it should be 8 rather than 7, even or odd. It doesn't matter, right? This is my degree in the graph. But the sum of degrees theorem says that the number of vertices with odd degree must be even. What that means is, this is real life I'm talking about. On Facebook, the number of people who have an odd number of friends on Facebook is even. This is a true fact. It must be true. Nobody actually knows what that number is because it's like too big to calculate, but it must be true that the number of people on Facebook who have an odd number of friends must be even. This is just a weird fact, and this arises in all kinds of, any graph you can imagine must have this property. I have recently heard, this is kind of, I hope you don't mind me using this as an example. This is kind of despicable, but when I was a kid, people didn't talk about this, but I've recently heard people these days like to talk about a person's body count. Are you familiar with this concept? I find this distasteful to discuss about a person in real life, but this is like how many sexual partners a person has had, all right? Now, you can view this in terms of graph theory. So every person is a vertex in this graph, and there's an edge if those two people have, counted the body, as they say. What this means, though, and you can add, I don't recommend this, but you can ask all your friends, hey, what's your body count? All right? Some people, it's even, and some people, it's odd. All right? When I was your age, mine was even, and I'll have you guess what the number was. 0 is an even number. When I'm a happily married man at this point. Anyway, some people it's even, some people it's odd. What this sum of degrees theorem means, this is a true fact. The number of people in the world with odd body count is even. It's true. And there's no real, in my opinion, there's no real reason, like, knowing what I know about human sexuality or whatever. Like, there's no actual reason why this should be true other than just a mathematical fact about graph theory. Strange but true. All right, that'll do. I'll see you all next time. Please let me know if you want to talk about the homework or the test.